While discussing contiguous memory allocation to the processes, we saw that it is plagued with the problems of external and internal fragmentation. So paging can be a possible solution for this, and in this paging technique, the physical address space of the process can be non-contiguous. So it's not necessary that the complete process will be put in one section of the memory only. It can be broken up into parts and put in different sections of the memory. So the process will be allocated physical memory wherever it is available. And this problem will avoid the problem of external fragmentation and also avoid the problem of the varying sized memory chunks like we discussed in an earlier video. So here the physical memory is divided into fixed size blocks called frames. So if let's say this is the RAM or the physical memory, so this physical memory, let's say this is of 128 kilobytes, this is for an example only, and we have a frame size of 32 kilobyte. So each frame over here, each section over here would be of 32 kilobytes. Then these would be called frames. So in the physical memory, these fixed size blocks are referred to as frames. And usually they are in the size is also in the power of 2, and the number of blocks then would also be most probably in power of 2's. And this size is usually varying from 512 bytes to 16 megabytes. Now this is about the physical address space. Similarly, the logical address space of the process will also be divided into blocks, and the size of the blocks would be the same size as that of the frames, but in the logical address space they will be referred to as pages. So if this is the logical address space, this will also be broken up into these fixed size blocks, and this size of this block would be the same as the size of the frame. So if the frame size is 32 kilobyte, then this block in the logical address space would also be of 32 kilobytes. But in the logical address space, they will be referred to as pages, and in the physical address space, they will be referred to as frames. The operating system now will keep track of all the free frames which are available in the main memory. So if we have a program which is having n pages in its logical address space, that means now n free frames should be available so that the program can be loaded. So let's say this main memory is having frames. So this is the RAM, and each frame is suppose having a size of 32 kilobytes, and if a process requires, let's say, 2 frames, that means let's say its size is 50 kilobyte. Since the size of the frame is 32 kilobyte, that means this process will now require 2 frames. Earlier in contiguous memory allocation, all 50 kilobytes would have to be provided contiguously wherever the memory was available. Now in paging, we will allocate non-contiguous memory space also. So this program, let's say P1 is of 50 kilobyte. So 32 kilobytes can be given over here in this frame. So let's say this is frame 0, and this is frame 1, frame 2, frame 3 and frame 4. So 32 kilobytes have been given to this process over here in frame 1, and another 18 kilobytes has been given in this frame 4. So now total of 50 kilobytes has been allocated to this process in 2 frames, but they are not contiguous. So wherever the frame was available, that process has been put, so the pages of that process have now been put over here. You remember that the pages of the process are of the same size as that of the frames. So one page would come here, another page can come over here. So the backing store can also be split into the pages. So wherever the process is stored, the logical address space over there would also be split into pages, and the backing store where it is stored, it will also be stored in form of the page size only. Now this technique can also result in internal fragmentation, though not in external fragmentation, but internal fragmentation can still exist. So how can that happen? Now this process required 50 kilobyte. So 32 kilobyte was used in this frame and 18 kilobytes was used in this frame out of this 50. So now out of the 32 over here, only 18 has been used by this process. So the remaining space over here is still leading to the internal fragmentation problem. Now let's see how address translation happens from a logical address space to a physical address space. Now any logical address space, let's say the size is of 2 to the power of m. This is the space available in the logical address space, and let's say the page size is 2 to the power of n. That means the total number of bits required for this logical address space is m. So the number of bits in the logical address space would be m. Out of this m, the page size is 2 to the power of n. That means n bits would be required to specify the page offset. How is that? So this is the page size. So let's see, this is the page in the logical address space. Now the page size is 2 to the power of n. Let's say the page size is 8 bytes. We are taking an example. So from the base, what is the offset of that particular address? Let us say the address is 12. So from the base address of that particular page, 8 is the base address, 12 is the required address. So from the base address, the offset is 4. So out of these 8 bytes which are available over here, the offset can be maximum from 0 to 7. And that offset, page offset, which depends upon the page size, can be represented by n bits. So the remaining m minus n bits would be specifying the page number. So we'll take an example for this. So let's say that we have a logical address space of size 2 to the power of 10. That means 1024 addresses, and the page size is 2 to the power of 3, that means 8. So like here we have shown 8 bytes each page is having, and the total number of addresses that are available is 2 to the power of 10, which is 1024. That means m is 10 and n is 3. So how many number of pages will be there in this logical address space? Whatever is the total size divided by the number of pages. So this gives us 2 to the power of 7, which is 128. That means from page 0 to page 127, that many pages will be available in this logical address space. Now let's say we have a logical address 22. So we know that the first 8 bytes will be over here, first 8 addresses will be here, the next set of 8 addresses would be here in page 1, the next set of addresses over here would be in page 2. If we look at this address, logical address 22, we know that it is going to lie in page 2 because it is from 16 to 23, the addresses are from 16 to 23. So 22 would obviously be lying in this page 2. Now what we have to see is how we can check whether how this binary address that is generated can give us the page number and the page offset. If you look over here, what is going to be the offset? So 22 is over here, the base address is 16. So from 16 we know that the offset is 6. But let's see how the processor or the system is going to interpret this. So this is the binary address that is being generated by the CPU. Because the logical address space is of size 2 to the power of 10, that means this address is of 10 bits. Out of these 10 bits, the page offset is of, the page size is of 2 to the power of 3. That means 3 bits will be required to specify the page offset and the remaining would be required for the page number. We can see in this example that there are a total of 128 pages. Size is 2 to the power of 7. So we know that 7 bits will be required for the page number and 3 bits for the offset. So if you take a look at the offset over here, you can clearly see that 110 refers to 6, and this we have seen over here that the address is at offset 6 from the base. If we look at the page number bits, we can see that this is specifying 0000010, which refers to 2, and we have seen that this address is going to lie in page 2. So from this address, the system knows that this address will be available in page 2 and the offset will be at 6 from the base address. Now what we have to do is we have to set up a page table to translate the logical address to the physical address. So the logical address is being generated by the CPU, and this logical address, while in the logical address space, all of these addresses and pages are contiguous, but when it will be mapped to the physical memory now, which is the RAM, and we are saying that we will give the pages wherever the memory is available. So that means there needs to be some mechanism to keep track of where a particular page is being put in the memory. So this page table will help us do that. This page table contains the base address of each page in the physical memory. So let's see, this is the page table for that particular process. So if, like in the previous example, we saw that in the logical address space there were 128 pages. So these 128 pages can be put in 128 frames of the main memory. So where exactly each page is being put into which frame, that information will now be maintained in the page table. So if there are 128 pages, that means 128 entries need to be there in this page table. So this will be the entry for page 0, this will be the entry for page 1, this will be the entry for page 2, and so on till 127. This will be the entry for page 127. Let's say page 0 was put in the available frame 5 of the main memory. So 5 will be stored over here. Let's say page 1, so this is giving you index, is giving you the page, and this is giving you the frame number. Let's say page 1 was put in frame 7 of the main memory. So this is how this information about the pages where they are being put in the main memory will be kept in the page table, and the page number will be used as an index into a page table. So this page number is being used as an index. So if I want to find where page 5 was kept in the main memory, so I'll have to index into this page table for the entry for 5. So this is 0, 1, 2, 3, 4, 5. 5 page number entry would be here. So here I have to index into this table to find out where the page 5 has gone and which frame it is available in. Let's say this is 1. That means page 5 has been put in frame 1. And this frame information along with the page offset information will be combined to give the physical memory address. Now you have to note that since the page size and the frame size is the same, that means whatever was the offset in the logical address, the offset will be the same in the physical address. So the offset remains the same because the page size and the frame size were the same. So this is how you can look at the paging hardware. So the CPU is generating the logical address, which comprises of a page number and an offset. Using this page number, it will be indexed, we will index into the page table. And where will this page table be available? This page table also will be stored in the main memory. Right now it is being stored like shown over here, but it would also be available somewhere in the memory. Now once we have indexed into the page table, we will get the information about the frame. So this was the page number, so it has indexed into the page table. Now this frame, along with the offset information, the offset remains the same. So the offset is being passed on as it is. So the frame information along with the offset information will generate the physical address, and that physical address now can be used to access into the physical memory. So now we know the frame, so that particular frame will be accessed. We know the offset, so we know that from the base address, this is the offset where that particular address, whichever address was generated by the CPU, that is available. So this is how paging will help us, and this is how the page table will help us map the logical address to the physical address. So let's take an example. So let's say m is equal to 4, that means the logical address space is of 2 to the power of 4 addresses, that means 16 addresses. You can look over here, there are 16 addresses over here. And the page size is 2 to the power of 2, that means n is equal to 2. That means the page size is 4 addresses. We are taking a very small example to explain the concepts. So this is page 0, this is page 1, this is having data A, B, C, D, this is having data E, F, G, H, this is page 2 and this is page 3. So we can see that since there were 16 addresses in total and the page size was 4, so the number of pages is 4. So we are having these 4 pages now over here. So page size is 4 bytes, and let's say the physical memory is of 8 bytes. So the physical memory is of 8 bytes. The page size has to be the same as the frame size. That means the frame size would also be of 4 bytes. So if the total number of addresses in the physical memory is 8 bytes and each is having 4 bytes, so that means there will be only 2 frames, frame 0 and frame 1. Now the OS is aware of the allocation details of the physical memories, which frames are allocated, which frames are available, what are the total number of frames. And this information is kept in a data structure which is called the frame table. So the frame table is keeping information about what all frames are there, which are allocated to which process and which are available. Now you can see over here that this particular page 0 has been put in frame 1 and this particular page 2 has been put in frame 0. So if page 0 has been put in frame 1, so then this information is available in the page table. The page table has been updated accordingly. If page 2 has been put in frame 0, then you can see, look at the page table, that it has been updated with the frame number. That frame number 0 is there for page 2. And since there are only 4 pages, there will be 4 entries in the page table, one for each page in the logical address space. Apart from the frame number, the page table also has a valid or an invalid bit. Let's say valid is being represented by 1 and invalid is being represented by 0. So if there are 8 pages over here, there will be 8 entries over here. For each page, there will be a frame number. That means page 0 has been put in frame 0 of the memory. So you can see that page 2 is available in this frame. So this is the physical memory. So this is the frame number, and we can see that page 2 has been put in this frame. For page 1, it has been put in frame 4. So in frame 4, page 1 has been put, and because it has been put, the valid bit is 1. If the page number is not been put in the memory or has been overwritten by some other data, some other block, then the valid bit would be 0. That means it is invalid. So right now you can see that pages 6 and 7 of the logical address space, they are invalid, they are not available in the memory, while the other pages, they have been put in the frames and the valid bit is 1. So the valid bit can show you that whether the information that is available in that particular frame is correct or not, is valid or not. So do we have internal fragmentation? Yes, we have internal fragmentation in paging as we just showed. Let's say the page size was 2048 bytes and the process size is this much. That means this process will require, because this is the page size, it will require 35 pages plus an extra of 1086 bytes. That means in the last page, there will be only 1086 bytes that will be used. So out of these 2048 bytes now, and these many being used, that means in that last page, this many bytes will be wasted. So what can be the worst case fragmentation? That in the last frame, only 1 byte was used. So that means out of all that one frame, 2048 bytes minus 1 byte, that is the worst case fragmentation. On an average, we can assume a half of frame size would be wasted in internal fragmentation. So if we have small frame sizes, because if we know that half of frame size would be wasted in internal fragmentation, that means we should reduce the frame size. But if we reduce the frame size, that means the page size will also decrease. If page size decreases, that means there will be more number of pages in the logical address. More number of pages means more number of page table entries, and that means the page table will become very large, and now this page table will require a lot of memory now. So all these things have to be taken into account. There is a trade-off for the internal fragmentation with the size of the page table. How can we implement a page table? So this page table is kept in the main memory. So let's say this page table is available in the main memory, and now every time the CPU is generating the logical address, it has to access the page table to find out where that address is available in which frame number. So how does it access the page table? How does it know where the page table is starting from? What is the address of this page table? So the address of the page table is kept in a register which is called the PTBR, the page table base register. So there will be a register over here in the CPU which will keep the address of the page table, and this address is pointing to the starting address of the page table, and from here now, depending upon the page number, it can be used to index into that particular page table. So every logical address that is generated now, there will be two memory accesses. One, you will have to access the page table to get the frame number, that this page is available in which frame. Once that frame is available, the physical address has been computed, then the actual memory address access would be required. So there would be at least two memory accesses for every memory access. Now this problem of accessing the memory twice for every address that is generated by the CPU is referred to as the two memory access problem, and this will require, when you are accessing the main memory multiple times, and we know that that is a bottleneck because accessing the main memory requires a lot of time. So this problem can be solved by using a fast lookup hardware cache. So there we can have a cache, and this is referred to as the translation Lookaside buffer, which is the TLB. So a part of the page table can be kept in the cache, this cache over here, TLB. So when the logical address is generated by the CPU, first the page table, the part of the page table which is available in the TLB will be checked. If this page number for this process was available here, then the frame number can be got, the physical address will be computed and directly we can go to the main memory. If it is a miss, that means this page number was not found in the page table which is available over here, then this page table in the main memory will have to be accessed. And some TLBs, they also use the address space identifier. That means that, so suppose multiple processes are running, so parts of page table of each process will be maintained in this TLB. So to see that this particular entry is for which particular process, so the address space identifier will also be available in the TLB entry. The TLBs or the translation look-aside buffers, they are cache, small caches, so they will be typically small, and if there is a TLB miss, then the main memory will be accessed for the page table. So if it was a miss for this entry, then this entry would be picked up and brought to the TLB. So if it is a miss, the value is loaded into the TLB for faster access the next time. So for this, again the replacement policies have to be considered. Now if we look at the paging hardware, so now the CPU is generating the logical address, the page and the offset. First of all, this page will be used, this page number will be used to index and to check the TLB. So now this TLB is having the page number as well as the frame number. So this entry, now since there are only, these entries are not contiguous entries, so this cannot be used to index into it. So parallelly, this page number will be checked in all entries. So let's say this is the entry for page number 3, this is the entry for page number 7, this is the entry for page number 2, and 3 is available in, let's say, frame number 0, 7 is available in frame number 1, 2 is available in frame number 8. So let's say this page was 2. So now we are checking this page number with all the entries in this over here. So this is being done simultaneously. So this 2 has been found over here. The frame number is available. So we say that this is a TLB hit. So now this frame number will be used over here along with the offset and the physical address will be generated. Let's say the page number was 8. Now if we look at the page numbers over here and we find that this 8 is not available, that means it was a miss. So now the page table in the main memory will have to be accessed. The frame number will be retrieved from there and this will be now used to compute the physical address. Once the physical address has been computed, now the physical memory can be accessed. So that means what will be the effective access time? We know that in case of cache, the access time depends upon the hit rate. That means what is the hit rate of the cache? That means how many times that particular address or information was found in the cache. So this is the effective access time formula. You can check my earlier videos on cache to take a look at this formula. So hit rate multiplied by the time taken to access the cache plus the miss rate, that means how many times it was not found in the cache, multiplied by the time taken to access the main memory. So if 10 nanoseconds is the time required to access the main memory, so if the desired page is in the TLB, then the mapped memory access takes 10 nanoseconds. That means it was found in the TLB. If it was not found in the TLB, what will happen? 2 memory accesses, that means 20 nanoseconds. So we are assuming that 80% is the hit ratio of the TLB. So what will be the effective access time? 0.8, which is the hit rate, into the time taken to access the TLB, which is the cache, 10, plus 0.2, which is the miss rate, which will be 1 minus 0.8, into the main memory access time, we are assuming that the main memory access time is 20 nanoseconds. So 20 nanoseconds. So this gives us 12. Now, if the page had been found in the TLB, it would have taken 10 nanoseconds. Since it was not found, it has taken 12 nanoseconds. So there is a 20% slowdown. If the hit ratio is slightly more realistic, 99%, then the time taken, effective access time would be 10.1 nanosecond. So only a 1% slowdown in the access time. So we see that how the TLBs, they reduce the access time of the memory. Because we have kept part of the page table in the TLB, so finding the frame number becomes much more efficient.